everyone. So a few days ago, OMC team compiled a mock for IOQM and we posted it on our server and sent to people on email. So this is the solution video to all the 2 markers in the mocks, and then there will be videos for 3 markers and 5 markers as well, just so that people know what the solutions are and what ideas behind the problems for. So let's begin. I'll turn off my video and just share the solutions part. So I hope you can see my screen. Okay, so let's begin with problem number 1. So it says for any number x. So basically, you are given a sequence of a1, a2, so on till an. Let's say it's a sequence of integers in which an is defined this way, and we're given that n be the number of values of k such that ak is 2023. Find the product of digits of n. Basically, we just have to find n. Only then we can find the product. So see, we are given that ak is equals to 2023. This means GIF of under root 2k plus half is equals to 2023. Now, using like basic properties of GIF, we know that if GIF of x is like, okay, I'll write it down. So we know that if GIF of x is k, this means x is in this range basically. Because if it's like greater than equals to k plus 1, then GIF will be greater than equals to k plus 1. And if it's less than k, then GIF will be less than k as well. So x should be in this range. So the whole problem is just based on this idea. So this means that 2023, yeah, let's maintain consistency of bench, is less than under root 2k plus half less than 2024. And now it's just calculation. So I'll not bother doing the calculations too much. So I'll just quickly tell the values. So this thing is 4090,506.25 is less than equals to 2k, which is less than equals to 2023.5 into 202.5. 4094 552.25. And since k should be an integer, okay, let's just divide by 2 first so that it's not confusing. So this would be something like 2047,276.125, and the other thing would be 4090,506.25 divided by 2, 2045, 253.125. Okay, so now since k is an integer, the minimum value of k can be 2045, 254, 2, 2047, 276. So the number of integers in this range should be 2023, I guess. Let's just do that. 2045, 254. Oh, 2022. Okay. So the number of such integers is 2022. One sec. Oh, right. So if we see that this number also satisfies and this number also satisfies the condition that AK is equals to 2023. So we have to count these two integers as well. In which case that would be like, let's see. Yeah, 2022 plus 1. Basically, it's like this minus this plus 1. So yeah, 2023 only. So the answer to this problem is like we have to find product of digits. So the answer would be 12. Just a second. Okay, so let's move on to problem number 2. Okay, I think it's better to put it below. Okay, let's start. Okay. So let the number of constant integers a less than equals to 2023 such that a is even and GCD of a comma 23 is 1. We have to find the sum of digits of n. So basically, let's just see which okay. So we have to see that which integers a are co-prime to 2023 and are even, right? So intuitively, when you would see the problem, you would feel that okay, maybe there should, so like let's say the number of integers co-prime to 2023 is 5 of 2023. Like 5 is the Euler-Torsion function. So like everyone knows this. This is like a famous lemma. And then you would think, okay, they're asking for even numbers, right? Like which of these are even? So we would say even and odd. Okay, so it should be like half of this, which is actually correct, but you still need to like, okay, in IOQM you don't need to prove it, but let's just see that why this is correct. So this is like the intuition usually. This can be wrong as well, but it's just not wrong in this case. So see, suppose GCD of k comma 2023 is 1. So see, we are saying that half of the numbers which are co-prime are even, which means you have to pair up the numbers in some way, right? So what is the most obvious pairing? Considering k and 2023 minus k. So see, you have GCD of this is 1. Let's now find GCD of 2023 minus k comma 2023. This would be GCD of 2023 minus k minus 2023 comma 2023. And this thing is the same as GCD of k comma 2023, which is 1. So if GCD of k comma 2023 is 1, then so is GCD of 2023 minus k comma 2023. And now k and 2023 minus k have different parity. Like if k is odd, then odd minus odd, this should be even. And similarly, you can do for even. So let's say you have a number which is co-prime and it's odd, then you know that 2023 minus k would be co-prime as well, but it will be even, right? So using this idea, it's just like half of 5 of 2023. And let's just calculate that. So 5 of 2023 will be 2023. And since the only prime divisors are 1 and 17, sorry, 7 and 17, it would be 6 by 7 into 16 over 17. Doing the calculations, it would give you divided by 7 divided by 17. This would give you 17 multiplied by 8 multiplied by 6. So this will be 816. And we have to find the sum of digits of n. So this will be sum of this is 15. So the answer to this problem is 15. Okay. Third problem, I think, is like a very, very appropriate IOQM2 marker. Like it does not involve much theory and not even that many calculations, but still needs some logic. Okay, what is happening? Okay. Huh. So we are given n is 99 factorial and we have to find the value of this expression, right? So what is this expression basically? It is 1 over uh, log 2n plus 1 over log 3n plus 1 over log 4n plus so on till plus 1 over log 99n. Okay, so what is the intuition behind this problem? You'd want to know that, like, you'd think that a lot of things would cancel out because it looks very not symmetric, but cancelable. Because see, n is 99 factorial. And if you see the basis of these logarithms, it's 2, 3, 4, so until 99, which is basically like how 99 factorial is made, right? Like if you take product of the bases, it will be 99 factorial. So it want that these things cancel out, right? And they actually do cancel out. Like there's this famous thing. Okay, before that, one thing you should see is all of these logarithms are different bases. So intuitively, you'd want to convert them to the same base, right? And you see that there's an n in all of these logarithms. Like you cannot do stuff with logarithms of different bases, but you can do stuff with logarithms of same bases. So what I would do is, I know that log a of b, sorry, yeah, I don't know how you say, log b base to a is 1 over log b, sorry, log a base b. So this thing would just be log of 2 base n plus log of 3 base n plus so on till log of 99 oops, base n. And then log a plus log b with same basis is just product of that. So it's just log n, 2, 3, so on till 99. So log of the numerator, this thing is 99 factorial, and base, we are given n is 99 factorial. This would be just 1. So the answer is 1. So a pretty simple problem. You just have to realize that you have to take same basis in logarithm. Like I think that is usually the case whenever you deal with logs. You would want them to be in the same base. Okay, let's move on to problem 4. Again, a logarithmic problem. So see, here the basis of the logarithm is the same. And you have to solve the equation, right? So you'd want to remove the logarithm. Like convert this expression into like some log of f of x. And then f of x is equals to this polynomial. And just solve that. That is a polynomial expression without any logarithms. So let's just do that. Okay, I don't know why I raised that. But anyways. So this thing would be, so 3 log x plus 1 would be log of x plus 1 cubed plus 1 is log 2. So this thing is just logarithm of 2x plus 1 cube. This thing is here. And now you just remove the logs because log is a monotonic function. So this implies x to the power 4 plus 2x cube plus 5x square plus 6x plus 1 equals to 2x cube plus 3x square 6x square plus 6x plus 1. Cancel, cancel. Oh, sorry. Here should be a 2. So here it should be a 2. So this expression would just become x to the power 4 minus x square minus 1 equals to 0. So now the standard thing, let x square be y. This implies y square minus 5 minus 1 is 0. It is a quadratic. So y should be 1 plus minus under root b square minus 4ac divided by 2a. And okay, so this is equals to x square. Y is x square, right? So it can be either 1 plus root 5 over 2 or 1 minus root 5 over 2. See, this is clearly negative. So x cannot be this, x square, which means x square is 1 plus root 5 over 2. So which means x should be, see, there's a catch here, I'll tell you. Under root of 1 plus root 5 over 2 or minus under root of 1 plus root 5 over 2. So these are the two possible values. Usually you just quickly rush over this and like mark the answer as 2. But I think the answer 2 is wrong. See, the thing here is log of x plus 1, which means that this thing should be defined as well. See, both the logarithms are defined for this value. So this is definitely a solution. What about this value? So, okay. This value, 1 plus root 5 over 2, is approximately 1 plus 2.236 over 2, which is 1.618, approximately. And under root of 1.618 is, I don't actually care. I just know that this thing is greater than 1. Like, it is exactly greater than 1. Not even greater than equals to. Like, if you want, I can calculate with a calculator and then give you the value. But that's all I need. It's just greater than 1. It's 1.272. Not useful for us. But anyway, so negative of this. Okay, let's not do it that way. So this implies negative of under root 1.618 will be less than minus 1. So this implies 1 minus under root 1.618 will be less than 0. So 1 minus under root 1 plus root 5 over 2 will be less than 0. So if I put x as this thing is just not defined. Like logarithm is not defined for negative values, right? Is it defined? Yeah, no, it's not defined. So this cannot be a possible solution. So the only solution is this. So this was the tricky part in this question. And I think like whenever you get the solution, you should check back in the original equation. Like even when you, for those people who know like what a functional equation is, this is why they suggest you like once you have found all the solutions, put it back in the original equation and show that all of those solutions work. If you do not show that, 1 or 2 marks get cut in a proof-based contest. This is why it's necessary. Like all the systems you find might not necessarily work. Cool. So the answer to this is 1, not 2. Okay, fifth question is, I think, sort of standard idea. Let's see the question. Array, I don't like this. Okay. Determine the number of pair of primes P and Q greater than 1 and less than 100. I actually do not think that this matters because they would not want you to bash out all the prime cases. Like, how many primes are less than 100? 25. So 25 choose 2. About uh 300 cases? No, they don't want to bash that. They want it to be clever. We want that all these numbers are prime numbers. So, what is the very basic argument with prime numbers? That if P is prime greater than 3, then P is congruent to minus 1 comma 1 modulo 6. And this question feels so much like that you have to use it. See, it says P plus 6 is prime and P plus 10 is also prime. So, like, obviously, modulo something you would think of some arguments. And the mod 6 is very nice for primes. So, let's see. So, P should be minus 1 comma. Okay. See, firstly, they just said that P and Q are primes, which means P is congruent to minus 1 comma 1 modulo 6. P plus 10 is also prime. So P plus 10 should be congruent to 10 plus 1 is 9. Okay, 10 minus 1, 9. Just 10 plus 1 is 9. Ignore that, sorry. I meant 10 minus 1 is 9 and 9 modulo 6 is 3, comma 1 plus 10 is 11, which is minus 1 mod 6. This is not possible because P plus 10 is prime. We would want this to be 1 or minus 1 mod 6. So this implies P can only be 1 mod 6. And you can just check that P plus 6 condition does not really matter here, modulo 6 at least. And we are done with this condition. Let's talk about Q. We know that Q is congruent to minus 1 comma 1 modulo 6. And if we check plus 4, this means Q should be congruent to Q plus 4 should be congruent to minus 1 plus 4 is 3 and 1 plus 4 is 5, which is minus 1 mod 6. But this is not possible. So the only possibility is Q is congruent to 1 mod 6. So we got that both P and Q are 1 modulo 6, right? And you can just check that this condition is also now useless. It will just give you the same that Q should be 1 mod 6. We're left with this condition. P plus Q plus 1. Since both are 1 mod 6, this should be 3 mod 6. Again, not possible because P and Q are, we have assumed that they are primes greater than 3 for now. And we got that P is 1 mod 6 and Q is 1 mod 6 as well. So not true. Okay. So now we got that P and Q cannot be primes greater than 3, which means P and Q can only be 2 comma 3, 3 comma 2, 2 comma 2, or 3 comma 3. See, if P is 2, then P plus 6 is 8, which is not a prime. So these two cases go away. If P is 3, this implies P plus 6 is 9, which is not a prime. So these two cases go away as well. So clearly, there is no such pair which satisfies the condition. So the answer to this is 0 such pairs. 0. Another 0. Okay. Okay, so now let's move on to question number 6. Let's take the first. Again. Yep. So the question says we have to find the sum of all the possible values of negative 1 by x plus 1 by y If x and y are real numbers not equals to 0, that satisfies this thing. Okay, so see, we can write this as x cube plus y cube minus x y cube plus 3x square y square equals to 0. This is a cube plus b cube plus c cube minus 3abc equals to 0 basically. Like, how do I motivate this? So, okay, eventually once you try this, you just see that there's no simple way to solve this, because it's not a quadratic or something that you can like write it as a quadratic in y and find some bounds on, sorry, write a quadratic in x and find some bounds on y. But you do see that there's like a cube. So, okay, like eventually, like at first you'd want to do something like x cube plus y cube minus x cube y cube equals to minus 3x square y square. And then something like want to write this as x cube minus 1 times y cube minus 1 and do stuff like that. But that does not work essentially. So you just see that, oh, at this point, it just looks like a cube plus b cube plus c cube equals to 3abc, right? So that is the whole idea behind the problem. So I can write this as a cube, where a is x, b cube plus c cube equals to 3abc. And so now we all know the factorization of this thing, a cube plus b cube plus c cube minus 3abc, right? It's just like a plus b plus c half times a minus b square plus b minus c square plus c minus a square equals to 0. So either x plus y equals to xy, this is one thing, or x equals to y and then y equals to minus xy and so on. So in this case, x times 1 plus y must be 0, which means that x is 0 or y is minus 1. And so if x is 0, this implies y is also 0. And if y is minus 1, this implies x is minus 1 as well. But both of them satisfied. So we get two more solutions. Okay. So now we have to find all the possible values of this thing, right? Also, one, this second, minus 2, 1. Yeah. So you can put back all the values in the original equation and see that like all of them actually work. So, and you have to find all the possible solutions to this, right? So minus 1 by x plus 1 by y in minus 1 comma minus 1. This thing is minus 1 plus minus 1, which is 2. For 0 comma 0, this is not defined. Okay, it just said that real numbers not equals to 0. So we discard the solution. And when x plus y equals to xy, this thing is x plus y minus of x plus y over xy. And we know that x plus y equals to xy, so this is just minus 1. So the sum of these two things is 1. So the answer should be 1. So it was basically just based on like factorization and like identity, and like just that you have to recognize it. Okay, let's move on to question number 7. Let x be the harmonic mean and y be the geometry of two positive numbers m comma n, such that m is greater than n, and we are given a relation between that. We have to find m by n. Okay, instead of m and n, I'll use a and b because that is more handy. So x is harmonic mean, right? Which means that uh, x is equals to 2ab over a plus b, and y is geometry mean, which is under root ab. So this implies AB equals to y square. So this implies x is equals to 2y square over a plus b. And we are given 5x equals to 4y. This means x is 4y by 5. This is equals to 2y square over a plus b. Uh, is this the best way to do this? Okay, rather than this, let's do this. Mm, okay, so we are given, okay, ignore this. We are given this. And we are given 5x equals to 4y. So this implies x by y equals to 4 by 5. Okay, why are we changing our approach? So what I wrote earlier was x equals to 2y square upon a plus b, and then x is equals to 4y by 5. And if I cancel out y, so I'll get the equation twice of a plus b equals to 5y. I want to find a by b. Like, I cannot directly proceed with this. Like, I do not have more information about y. All the information I have used it. So, like, you would possibly want to write an equation which involves only a and b because you want to find a by b. So, if you find an equation which involves only a and b, then you can manipulate some things by like dividing by b or something like that to get a by b in that equation. So that is why if you write x by y, we'll see that we can just write then x as 2ab over x plus y and y as under root ab. Oh, extremely sorry. This should be a plus b. 2ab over a plus b and then y is root ab as 4 by 5. And this becomes 2 root ab over a plus b. And now this is just an equation in a and b. There is no y here, unlike here. I mean, I think you can probably like manipulate this and like put y as, oh, you could do that. Okay, useless. You can just put y as root ab here and you'll get the same thing. But okay, we get the same equation. Uh, we want to remove the root, so we'll square this. It's just like standard equation solving idea. 4 by 25. This means 25ab should be 4a square plus 4b square plus 8ab. This implies 17ab equals to 4a square plus 4b square. See, we want to find a by b, right? I think it is a standard trick. I don't really know how to motivate this, but to convert this equation in terms of a by b, okay, either you can do this. Consider it as a quadratic in a. Like this is a quadratic in a, and find a in terms of b, and then find a by b, which is slightly longer. So what I do is I just divide by ab. Sorry, b square. So this becomes 17a by b, which is equal to 4 times a by b squared plus 4. And now I can let a by b as my x. So this implies 4x square minus 17x plus 4 should be 0. And from here you get x equals to 4, 17. Yeah, 1 by 4 or 4, which implies a by b is either 1 by 4 or 4. Now see, we are given a is greater than b, which means a by b must be greater than 1. So the answer should be 4. Cool. So the main idea was to like try to manipulate the values, find an equation in a and b. That was the main idea. And then try to manipulate that to solve it. So answer is 4. This was question number 7. Okay, I think I'll write here rather now. Let's do question 8. Question it, when I saw it for the first time, it looked sort of scary. But this is the kind of question where you have to trust the process. Like you have to do the most intuitive thing, which does not look that it works, but you just have to trust it and like keep on doing it. So, like, what is the most basic thing? Uh, you just take the LCM, like without noticing anything. So the numerator is okay, without not noticing, but like it's like when you take the LCM of the first thing, it's x plus y plus z over xy plus xz equals to 1 by 2. The second thing is x plus y plus z over yz plus xy equals to 1 by 3. So basically, the noticing thing here is if you take the LCM and like do this, all the terms have x plus y plus z in their numerator, which is sort of nice, right? So let x plus y plus z be equals to 3. Oh, not 3, sorry. Be s. Then 2s equals to xy plus xz. 3s equals to xy plus yz. 4s equals to xz plus yz. And this is a very standard thing. Like you can write xy as a, xz as b, and yz as c. So you have a plus b something, a plus c something, and b plus c something. So what do? You take sum of all the three things. So you get 2 times xy plus yz plus zx equals to 9s, which means xy plus yz plus zx equals to 9s by 2. And now you can subtract this from this to get mm, xy plus xz. Yz equals to 9, 4.5, 5s by 2. And do that for other two equations as well. So xy, yz, xz would be equals to 3s by 2 and xy equals to s by 2. Again, this is also a standard thing. You just take product of everything. So x square, y square, z square equals to 15 s cube over 8, which means xyz is equals to s over 2 under root 15 s over 2. Okay, this looks slightly weird. Huh. Okay, so now we divide like this from this. So you get x is s by 2 over 15 s by 2 divided by 5s by 2. Okay, my 5 and s slightly look similar, so bear with that, please. So this would be 1 by 5 under root 15 s by 2 is x. And similarly, you'll get that 1 by 3 under root 15 s by 2 is y. And 1 by just 1 under root 15 s by 2 is z. Now, you still have an s. Do not forget that. What was s? It was x plus y plus z. So basically, you see that this term here is in all the three things. So if we add it, we can take this out common. And if we add that, we get an under root x plus y plus z on LHS, but an x plus y plus z on here also. So we add all these things. So we get under root 15 x plus y plus z over 2 times 1 by 5 plus 1 by 3 plus 1 equals to x plus y plus z. So this would become like under root 15 by 2 times 15, 3 plus 5, 8, 23 equals to under root x plus y plus z. So this implies x plus y plus z is equals to uh, 15 over 2 into 23 square over 15 square. 23 square over 30. Right? So now x, so okay, we have to find x, y, z, right? We need this thing, under root 15s over 2. This would be under root 15 times 23 square over 30 times 2. So this is 23 over 2. So which means x is 23 over 10, y is 23 over 6, and z is 23 over 2. What do we have to find? 1 by x plus 1 by y plus 1 by z. So 1 by x plus 1 by y plus 1 by z would be 23 over 10 6 2, 10 plus 6 plus 2 over 23, which is 20 over 23. This is p by q. So we have to find p plus q, which is 43. So the answer is 43. So it was like all like once you notice that after writing the LCM, everything becomes standard. Like you can just take the reciprocal and it converts to this form, which is a standard thing. This idea is also standard once you get x, y, y, z, z, x, and then you just find x, y, z. And then you notice that s is x plus y plus z. And how can I get x plus y plus z on the other side to find that? So sort of standard ideas, but you just have to like go through with it and like trust that eventually the stuff should work out. Okay, let's move on to the last two problems for 2 markers. Problem number 9, let's do that. So if the angles of triangle, I'll put the problem. So it says that in triangle ABC, the angles are an arithmetic progression. So they're of the form A minus D, A plus D. Okay, this much only. We know that sum of angles of a triangle is 180, right? So that will just give you A is 60. So the angles are 60, 60 degree minus D, and 60 degree plus D. And you are given AC is root 3x and AB is root 2x. You want to find measure of angle A in degrees. Okay, so we can just assume D is greater than 0, there is a symmetric thing. See, clearly AC is greater than AB. This implies angle B must be greater than angle C. So, if angle B is 60 degrees, then angle C can be 60 degree minus D. If it is 60 degree plus D, then it can be 60 or 60 degree minus D. And if it's 60 minus D, then it's the least angle. So that case is not possible. Okay. So let's see this case first. Angle B is 60, angle C is 60 minus D. So by sine rule, sine of angle B, which is root 3 by 2, times sine of angle C must be root 3 by root 2. Which means that, uh, sorry, 1 by root 2 should be sine 60 minus D. And since this angle is in the range 0 to 60, like 60 degree minus D would be in this range, no? Because it's an angle, so it should be greater than 0 and D is positive. So it must be less than 60. So this implies 60 degree minus D should be equals to 45 degree, which means D is 15 degree. This gives angle A to be 75 degrees. So one answer is this 75 degrees. But let's just check the other cases. So when I was making this problem, I basically thought that this is the only solution and the other solutions do not work. But apparently there's one more solution. So the problem is actually wrong. It's a bonus question. I'll just show you the other solution. We will not go into much details of that. ABC. So let's say this angle is 60 plus D and this angle is 60 minus D. Then you have that sine of 60 plus D. By the way, in this case, this angle should be 60 degrees. Sine of 60 minus D should be root 3 by root 2. So now if there exists some D such that this thing is true, then A can be 60 degree as well, right? And I'm not proving it here. Like you can ask in comments or on DM to me later. But you can basically show that this thing, unless I'm wrong, uh, this thing is surjective over 3x plus. Yeah, r minus minus 1. So basically, this thing can take any value from, what do you say? Array. Yeah, any real value except minus 1. So there must exist some d for which sine of 60 plus d over sine of 60 minus d is root 3 by 2. And by some bounding stuff, like I'm not going into much details of that bound, but you can basically show that the d that you'll get will be less than 60 degrees. They're obviously positive, but less than 60 degrees. So there will be such a d which satisfies that both these angles exist and angle is 60 degrees. So basically there are like two solutions, 60 degree and 75 degrees for A. Okay, I'm actually not try this case. Let's just see if this case what we get. ABC 60 plus D 60 root 2x root 3x. So you'll have sine of 60 plus D over sine 60, which is root 3 by 2, must be equals to root 3 by root 2, which means sine of 60 plus D should be 3 over 2 root 2. Mm, okay, how much is this then? 2.8. Isn't this greater than 1? Wait, did I mess up somewhere? Root 3 root 2 sine 60 is. Yeah. Okay. So this thing is like greater than 1, so this is not possible. Yeah. So this case is not possible. And 75 case was obvious, but this hidden case was also there. So there are two possible answers, but the question that says that find the measure of angle in degrees. Like I could have said that find the average or something like that. It would have been fine. But since it says find the measure, the question is wrong. So bonus. Enjoy. You get 3 marks for that bonus. I think in the answer you'll just like grade everyone out of like 100 minus the bonus points. Okay. This question is a nice question. So let's talk about intuition in this. So basically, what is there are 10 children, C0, C1, C2, C3. We are not talking about combo as well. We're not considered with that. Bad joke, but I wanted to say something because I was bored writing this. Anyway, so yeah, these are the 10 kids sitting in a circle, and teacher gives sweets such that like it gives first sweet to C1, leaves one kid and gives next sweet to C3, leaves two kids, gives to C6, leaves three kids, gives to C0, and keeps on going like this. Let A be the set of all I such that child CI does not receive any sweet. Teacher goes on indefinitely, by the way, because it's not specified. So yeah, just assume that goes on indefinite. Like you do not just, I think yeah, it's sort of suggests she continues in this way and never said that when she stops. So it just goes on. We have to find the sum of all the elements in it. So see, we know that the set A is finite, and since it's like the set is findable, like obviously it won't be the set of all kids because like these kids definitely do get a chocolate, right? So eventually there must be some pattern, like let's say that C2 receives the sweet at like some 10,000 step. That is very unlikely to happen. Like they should be noted that there is only 10 kids and teacher is following a given sort of pattern, right? So that after like some 20, 30, 40 moves, you should be able to determine which kids receive sweets and which kids do not receive sweets, right? So it's basically trying to find that pattern in which the teacher is giving sweets. Oh, just a second. Yeah. So it's just like about finding that pattern. Let's see what the teacher is doing basically. So in the first move, she gives kids to sweet one. Then plus 2. it gives to third child. Then plus 3, it gives to sixth child. You can see the arrows mark. Then plus 4, it should be given to 10th child, but there's no 10th child. So it gives to 0th child. Then it will be plus 5 and given to 15th child. But there's no 15. So like 1, 2, 3, 4, 5, fifth child. We can just see that this is mod 10, right? Like there are 10 children, so everything is just mod 10. So basically, first sweet is given to 1. So, first sweet is given to first kid. Second sweet is given to 1 plus 2. Third sweet is given to 1 plus 2 plus third child. So basically, kth sweet given to 1 plus 2 plus so until kth child modulo 10. Which means kth sweet is given to k plus 1 by 2th child modulo 10. And clearly, this is like k square plus k by 2. This is a polynomial. So this should be like eventually periodic modulo 10. And yeah, like the period of the periodicity should not be that much as well because it's like modulo 10. So you can manually bash out and convince yourself when it starts to repeat because it's, I think, only like 20 moves after which it starts to repeat. But I'll give you a formal approach. So see, it's k plus 1 by 2 modulo 10, right? So if we consider k plus 10, yours mod 10. So one will consider k plus 10. Then this thing is k times k plus 1 plus 10k plus 10 times k plus 10 plus 1 by 2. So this is k times k plus 1 by 2 plus 5 times 2k plus 10 plus 1, which is 11. Modulo 10. So this is not very good, right? Like you get a 5, but you want something like a multiple of 10 here to cancel out with 10. So like 10 was intuitive to take because we are dealing with mod 10. So now we want, we see that this gets divided, the 10 gets divided by 2 to get a 5. So if we take 20, here it will be a 10, which is good. So k plus 20, k plus 21 by 2 is congruent to k plus 20 plus 1. Let's do this. K times k plus 1 by 2 plus 10 times, let's see. Okay, 10k plus 10k plus. Okay, unless I did calculations wrong, it should be something like this, modulo 10. And since this is 0 mod 10, this is just k plus 1 by 2 mod 10. Which means if kth suite and k plus 20th suite are given to same child, we can also repeat this argument for k and k minus 20, right? Oh, wait, not k minus 20. Uh, let's see, 20. I think we can repeat this argument for 20 minus k. Okay, let's try. If it does not work, then I'll just tell. But let's see. Like if this works for k and k plus 20, you would expect, like, hopefully, that if it works for kth and 20 minus kth as well. So let's see, 20 minus kth suite will be given to 20 minus k into 20 minus k plus 1th child modulo 10. This is 400 minus 20k plus 1 minus 20k plus k plus 1 by 2 by 2 mod 10. Bro. Yeah. And this is 0 mod 10, obviously. So this is k times k plus 1 by 2 mod 10. So basically, kth, 20 plus kth, and 20 minus kth, all these suites are given to the same child. So now, If I talk about the first suite, second, so on till 20th suite, then I know 21st suite will be given to the same child, right? So I just want to find which child never receives sweet. So I can just find which child never receive sweets if only 20 sweets are distributed. Because after that, it's just like like periodic. So if child, let's say child zero did not receive any sweet in the first 20, it will never receive any sweet. Okay. And even in this, we can shorten our argument. Like if 1, 2, so until 10, 11, 20. We know that if k receives 20, k and 20 minus k sweet is given to the same child, right? So first and 19th sweet. Yep. So wait, I'm doing it correctly. K plus 1. Yep. So the first and 19th sweet will be given to the same child. Second and 18th sweet will be given to the same child. So I can just take 1, 2, 3, so until 10 and 20 also. So I can just take these sweets number, like which kids are receiving these sweets. And I know that these sweets will be the same as like the child receiving these numbered sweets will be the same as the child receiving these numbered sweets. So my answer still won't change. I can just check for this. So these are just 11 values. Not hard to check. And unless I'm wrong, I think I have that written in my solution. I'll just check from there. Yeah, I'm lazy to bash out the values. So it's like we can like bash out these values, like which children receive these sweets. So children 2479 do not receive any sweets. So the answer should be 22. Ignore the answer. The main part is seeing what the teacher is doing. Like it is giving k plus 1 by 2 modulo 10 children sweet. And then it's like you want to find some pattern, right? Like something periodic. So as to narrow down your bash. So the most intuitive thing is to consider k plus 10. But that gives you 5 here, which motivates to check k plus 20. So k plus 20 receive the same thing. Now, I think in exam, I would just go with like checking the first 20 values. It's not that much work. But if you still have a lot of time and like luckily you observe this quick enough, I think it's good for you. At least in proof-based exam, you should like see this because there's a lot of time that k and 20 minus k would also receive the same. Also, this is sort of motivated, right? Like k and 20 plus k receive the same. So why not k and 20 minus k? Because modulo 10, not much has changed except k becomes k minus k. But when you multiply two negative things, it becomes positive because we're multiplying two things. Okay, a very bad way to state thing, but that is how I would say the intuition would work. So the answer is 22. And with this, we are done with our two markers. If you want, I can write out the two markers answer key here somewhere. Uh, so let's see. Problem 1 is 12. Problem 2 is 15. Problem 3 is 1. 0, 1, let's say. Problem 4 is 11. Sorry, that's 1. So 0, 1 again. Problem 5 is 0. Problem 6 is 0, 1. Oh my god, too many zeros and ones. Problem 7 is 0, 4. Problem 8 is 43. Problem 9 is bonus. Problem 10 is 22. So this was the video for all the two markers. Next video will be for the three markers. So I hope you enjoyed the solutions, and if you have any doubt, feel free to comment it.